Ladies and gentlemen, distinguished visitors and auditors, it's my great pleasure to introduce you to Mr. Avik, who came to us from the distinguished group of Professor Noah Cowan at Johns Hopkins in 2009, 10, and has worked in quite a diversity of projects, some fraction of which we'll see in his dissertation defense. And it's my great pleasure to cede the floor to
And let me just ask everybody to ask clarification questions during the talk and more substantial questions at the end of the talk.
So after time for 45 minutes, is that right? Yeah, thank you all very much for coming. Yeah, so I guess I'll just jump into the motivation. The motivation in working in robotics for me has always been to kind of have an impact of some kind. So the motivation's really always been robotics that's commercially viable, not just stuck in the lab. And as some of you know, I've also co-founded a company at my time here to kind of try to speed that process along as well. But to kind of look at where commercially viable robotics is, so should I try to dim these lights or can you see?
I can do it.
There's a preset.
Yeah, so I've tried to plot kind of the effectiveness that robots have outside the lab today. And yeah, there are some very effective robots. People are very happy with their Roombas, and people are probably going to be very happy with their delivery robots as they bring their pizza to them. But the effectiveness of the robot starts to go down quite a bit as you get into tasks that are slightly more complicated. So we've been thinking at the company of having a robot that helps in agriculture. These rolling vineyard hills would be quite challenging for a robot today. Even worse would be a disaster area like this, where we'd certainly not like to send people. And even worse is kind of this indoor power plant where there are stairs, narrow walkways, which are completely very simple to something like a night watchman, but be very challenging for a robot. So we're going to build robots that are aiding people, replacing people who have to do boring and dangerous tasks. We really need to think about these issues. So why am I saying that we should kind of go back to square one and think about mobility? Because that's really kind of what I was doing. As you saw, the terrain was getting more challenging and our effectiveness was kind of going down. So the first question that you might ask is this a solved problem? So these four kinds of robots would have all been on the effective side of the robots we've seen be successful in the world today. So certainly factory automation is very good. All of our cars and things like that are produced by robots, and they do a fantastic job. The Roombas we talked about. Here's AlphaGo defeating the world's best Go player. And here's DJI, who's made a really big impact in aerial photography. So what's the secret? Why are these kinds of robots successful? Versus, so here's, I'm not going to show videos of the DRC. You've all seen a nauseating amount of them, but yeah, in the DRC, it wasn't a rousing success by any stretch. So what's the gap here? My argument is that the places where robots have been successful, they've had very structured environments. So the structured factory floor, the living room floor, no environment at all. The robot's just living inside an electrical computer, and the sky. Also turbulent wind and things like that pose problems as well. But for the most part, it's not as bad as this. So structured environments is a thing that seems to have been helpful so far. But really, what we'd like to do is try to remove some of those safety harnesses and kind of build robots that have structural stability against environment and parameters, because the real world is messy. The second question you might ask, having kind of posed that first motivation, is why wouldn't you use learning to achieve some of these goals? It seems to be a hot topic these days. So my second counterpoint is, now that we've looked at this locomotion challenge that we didn't do well at, I want to take you back 30 years and look at the locomotion successes from 30 years ago, where Raibert kind of showed us how to dynamically hop and run. So why can't we use some of this knowledge and put it in this robot? Why is that, to a layperson, why is that problem hard? So the problem is hard because the locomotion, we can't build algorithms that are just for specific tasks. We should focus instead on building solutions that are generalizable, so that we can do things like use the knowledge of Raibert's robots hopping inside the lab with large power source, and somehow take that knowledge and put it in the DRC robot. So we need some way to do that. And the third question you might ask is, why would anyone else care about all these things I'm saying? I'm really talking about mostly locomotion for the moment. So my answer to that is that legged locomotion is one of the research areas where, if you don't think about all of these issues, all of the first two issues, structural stability and generalizable solutions, the robot literally falls on its face and you're kind of forced to deal with those issues. Whereas if you don't have structural stability, but you have a robot that's not a legged robot, there's a fair chance that you can move on, but really we'd like to address these issues, and legged robotics kind of brings them to the forefront. Okay, so my contributions in this thesis, this is figure 1.1, the very first figure in my thesis document, and what I've tried to do is, not to overwhelm you, but what I've tried to do is give you an overview of where my contributions have lied, and I'll try to use this as kind of a guiding framework to take you through the presentation as well as the thesis document. So on the left here, we have a variety of models of robot bodies, essentially. And you can see that there's some diversity in the morphology. They're all fairly simple. They're models from the plane, but they range from these bipeds to these monopeds. Some of them have a tail. So there's some diversity there. But the interesting thing is that the control strategies for all of these are constructed from a largely overlapping number of primitives. So what I'm trying to develop are solutions that are generalizable across this diversity of bodies. And along with all of these synthetic contributions, there are analytical as well as numerical and empirical results. So yeah, so now I spent hours on that animation, but yeah, this slide took a long time, but hopefully it's worth it. So in terms of the contributions as in terms of how useful the contributions will be to the general robotics public, I think first and foremost will be the empirical contributions. So the key words here are that these contributions are the synthesized robot behaviors are robust to both parameter perturbations as well as state perturbations. So I've given you a cartoon or a visual description here of one of them, where the robot is being subject to large kind of vertical perturbation in one of its strides as it moves, and it recovers. So this is an example of state perturbation, but also when the controllers are synthesized, they need very, very crude models of the robot bodies themselves. So the algorithms are also very insensitive to model perturbations. The second area of contributions lies in the analytical results. So what I've developed is really a formal way of thinking about the synthesis problem, where we think about synthesizing these behaviors on robot bodies from these simple template primitives, a problem that, an approach that even Raibert used 30 years ago, but it's taken a long time to kind of formalize how to think about it and also get formal guarantees about the results. And the third is a set of conceptual advances, which I've actually kind of broken out here. The first is that given this argument that I made that we can think about synthesizing these bodies from these templates, there has to be some way that has yet been not known of how to kind of compare these two columns. So how is it that this kind of slot hopper body is really similar to these templates that I'm trying to synthesize them from? We finally now articulated some relation between these two columns that lets us actually verify that the work we did is what we wanted. The second conceptual advance is this idea of generalizability. For instance, in this row, you'll see in the first three rows, actually, you just see these three templates show up, and I'll talk about what these mean in subsequent slides. And they've been able to synthesize behaviors on these three very, very different looking bodies. That formal procedure of taking simple templates and anchoring on different bodies is a new conceptual advance. And the last conceptual advance is what I call in one word tuning, but it's this process by which, before we were restricted to kind of thinking about how to, there's the roboticist here, there's some synthesis procedure. In my case, that consists of thinking of a bunch of templates that constitute a behavior and somehow pushing them onto the robot body. But there's no feedback. So if the procedure fails, we wouldn't know what to do. But now we're slowly starting to add information back along these arrows such that we can get information both about the parameters here in the body as well as about our mistakes here when we're selecting the templates that can help us have feedback and close this design loop. Mostly, for the moment, this comes in the form of analytical formulations of the final stability criteria. And they tell us how to modify design parameters as well as control parameters such that our synthesis succeeds. So I'll also use this to kind of develop the outline for the talk. So first, I'll talk about the robot bodies themselves. A lot of the work that I've done, non-conceptual work, has kind of thought about, well, actually also conceptual work, has thought about how the robot bodies have to be constructed such that this kind of generalizable synthesis is possible. I call this the development of high bandwidth electromechanical systems, and some of these systems are described here. There's a quadruped and a tailed biped. Next, I'll talk about correct by design compositions, which is the main contribution, and I'll use a few examples. So I'll talk about SLIP, which is a 2 degree of freedom pogo stick, the slot hopper, which is a 2 degree of freedom biped, and this Jaguar robot over here. And finally, I'll have a conclusion. So first, let's talk about the hardware design. Right. So here's a video of Roger Federer hitting a forehand. So the reason I show this is there are actually many reasons. So the first reason is that so the tennis player can do this, hit this perfect forehand regardless if he's running towards the net, away from the net. There's some notion of primitives, and biomechanists call these synergies. It's a way of reducing dimension in the number of control signals from the neural system all the way down. That kind of reduced dimensionality, and the tennis player doesn't have to think about how every joint in his body moves. And he also has the knowledge of combining these primitives, these synergies, with other primitives, such as running towards the net, away from the net, etc. So it's important for us to be thinking about compositions and generalizing solutions to be, hope to match up to animals' performance. The second reason I show you this video is that the sensory motor update rate for a human is something on the order of 8 hertz. So there's a sensory motor delay of something like 150 milliseconds. And somehow he's able to do these really amazing things. But one of the reasons that our robots can't really do as well as the animals can is that the animal has successfully distributed his control effort, not just in his electrical or neural system, but also his mechanical system. And we don't have that kind of granularity in our robots yet. So the control loop, which is at 8 hertz, doesn't go all the way from the tennis ball to the brain. There are many different control loops that we can't see, and it will be a very bad mistake for us to think our robots should have, can have all of these control loops, can have this kind of granularity to be able to emulate this. So instead, what we did with our robots is gave them the bandwidth all the way from the end effector, sensing to actuation. That's a kilohertz. I mean, there are some mechanical delays, but we try to speed those things up as much as we can so that we can embed these primitives. The primitives in the animal are really embedded by a combination of hardware and software, but really we don't have that kind of granularity, so we have to try our best to have high bandwidth as much as possible. By the way, this door opening was work by Turner Topping. And here's Turner again, demonstrating another very important aspect, which is transparency. Transparency is, this high bandwidth has to show up in a variety of components on the robot, going from sensing to communication, to computation, to transmission, to actuation. And so while we talk about actuation here, sensing is also a huge part of it. And one of the fastest modes of sensing we have is proprioception, where essentially forces perceived from the environment are transmitted back to the central processor very fast. So there are very little delays here, and we've tried to emphasize and improve the quality of that signal quite a bit in our robots, such that you can see that it can perceive even very small forces at the end effector. And we use those ideas to kind of, this is a bounding gate where the robot is using very fast sensing of forces at its toe to very effectively emulate some of the control strategies I'm about to show you. Okay, I'm not going to, I motivated the design part, but I'm not going to tell you about our solutions except for a very brief overview because there's not that much time. But some of the contributions take, the flavor of some of these contributions include, for instance, thinking about models of actuators to really understand how our design parameters affect some of these performance criteria like bandwidth, these kind of nebulous performance criteria like bandwidth and transparency that we want to really get at. So, for instance, we've been able to do things like relate the design parameters of a motor to the power and force criteria at the output. And the implications of some of these things are that we understand the physical limits of DD stands for direct drive, which means that there's no gear reduction between the actuator and the end effector. And obviously, having direct drive improves bandwidth and transparency, but it's harmful in some other ways, and results like this let us understand physical limits in this space. We also came up with metrics for guided selection of actuators for some of these criteria. Similarly, so that was the actuator. Now moving kind of slowly down through the body. Similarly for the drivetrain, we came up with dynamic task classification ideas for gearboxes, so that we think about not just static tasks, which is kind of the trend in industry, stalled or continuous speed operation, but really dynamic tasks such as jumping or leaping or things like that that'll really affect these selection criteria in a drastically different way than static selection criteria. So for instance, one of the results we had is that with this dynamic task specification, it's necessarily worse to have intermittent operation, than continuous rotation in an electromechanical system. And as you might anticipate, the legged systems must have intermittent operation unless there's some fancy flywheel transmission system. Moving further down, we've thought a lot about leg design. Manipulability criteria have existed for a long time for manipulators, but we've kind of enhanced these criteria by adding things like proprioceptive sensitivity, so that we can tune these manipulability criteria or enhance them for our use for high bandwidth electromechanical systems. And the last thing is platform design. So I'll talk just about the small platform Jerboa, even though there were a whole family of direct drive robots that we created at Penn. So this robot's very interesting because it has a very powerful tail actuator that has 2 degrees of freedom. So you can see that there's a spherical joint here driven by 2 motors. And the design of this robot was guided very much by concepts such as self-manipulability. So self-manipulation is a concept articulated by Aaron Johnson previously in this lab as an ability of the robot to exert, or impart forces on its own center of mass, leveraging contacts with the environment. So the very interesting thing about the tailed robot, tail morphology, is that you can see that it has many more contact modes and affordances available to it compared to a simple 2-degree of freedom leg. So this robot has very simple legs. There are 1 degrees of freedom, and we instead chose to use the mass budget for actuators on the tail instead of on the leg. So what are some of the benefits that we can get from a tail instead of putting all of our motors in our legs? So for one, tails are very useful for hopping, as I'll actually show you in this slide. And here's the namesake for this robot, the lesser Egyptian Jerboa, doing a similar hopping. Who knows if it's using the tail the same way? Probably not, but it was very helpful for our hopping behavior. Tails are also very useful for reorientation. Here you can see there's a gecko for inspiration here, and the robot's able to correct its body attitude in flight, which would be impossible with massless legs, it would be very difficult. Actually, it would be impossible unless there was some mass in the legs. And lastly, tails have also been used for actually leveraging contact with the ground. So you can see that the tail on the robot on the right is used to exert forces to help the leaping behavior. And this is also sort of bio-inspired. You can see the kangaroo also uses its tail as a contact for walking. Yeah, so that's all about design, and I couldn't really do it justice, but I really want to talk about some of the composition ideas. Okay, so what does this mean? So what does it mean to kind of think about compositional gate design? So here's the classic templates and anchors figure from Full and Kodacek, where we're describing the process of kind of looking at animals. So this is an analytical procedure where we look at a complicated animal called the anchor here, and try to understand why, when an animal is running, it seems to exhibit much fewer degrees of freedom than it really has. So a human or a horse running across a horse plate will look like it's a pogo stick to the observer, but really we know it has a lot of other degrees of freedom. So what's it doing to collapse those degrees of freedom? And I was actually interested to think about this procedure in the opposite direction, where my robot body is complicated, but I have kind of these simpler perspectives of what it should be doing. So for instance, let's say I'd like my robot to hop up and down. It's a kind of a very obvious requirement for dynamic locomotion. And let's say I want my robot to exhibit this behavior. So this is a picture of Raibert's planar hopper from 1986, and somehow I want my planar hopper to look like it's a vertical hopper in some situations. But that's not all. I'd also like it to control its fore-aft speed as it moves on the plane supported by the boom, and maybe I need to embed a different primitive onto it. So my perspective as a behavior designer is that there are a collection of these primitives, such as hopping up and down and translating in the plane, that I'd like to simultaneously embed on my robot body. So that's kind of the perspective I want to take of synthesis. And like I mentioned before, this idea of kind of thinking about primitives and how to combine and reuse them on the robot body has been thought about a little bit in literature, but it's not typical. It's not a conventional way to think about synthesis. All right. So what is the desired effect? So the desired outcome is that firstly we'll have these dynamic locomotion behaviors. So here's the tailed bipedal robot kind of hopping happily along on the plane. But the other part is that we want these ideas to be generalizable. So there were some templates used to develop the control strategies for this behavior. We'd like to use the same ones as much as possible, generalize that knowledge, and use it for a different platform. And that's actually what we were able to do. So this bounding behavior uses very much the same control strategies as the planar hopping behavior with the tail. And here's another platform, a monopedal hopper that we've worked on. And again, it uses the same control strategies as the other two. So the reason I chose these three is that they're very different morphologies, as you can see, but we really want to think about this generalizability. All right, so how were these controllers synthesized? So I like to think about these controllers as not just controllers standing on their own, but they're really these dynamic primitives. So for instance, here's an example of a dynamic primitive. It's or also known as a template, so I might use those words interchangeably. So it's really a 1 degree of freedom dynamical system. That's, it's got some states, it's got a control input, but really for the first perspective of this thesis, we're thinking about these primitives as closed loop dynamical systems. And somehow I'd like to put this closed loop dynamic system into my robot. So the point of this primitive, point of thinking about this primitive instead of the full robot is that it's very easy to synthesize a controller in this perspective, in this simpler body. Similarly, if I asked you to think about how to synthesize a controller for 4-app speed control, you might have to think about it for a bit, and it wouldn't be very challenging. So, for instance, this is Raibert's idea for how to control 4-app speed of a monopedal hopper. So the key thing that you should look at here is how the leg is being positioned right before touchdown. So this is theta, the leg angle, and you can see that it's being positioned somewhere close to this orange dashed line, and that's what's key in controlling its 4-app speed. And lastly, if I give you an isolated rigid body and the ability to exert torques on it, it's fairly simple to think about how to stabilize its orientation with a PD controller of some sort. So now let's get back to the examples I showed. So here's the tailed hopping robot. And really what we do intuitively is kind of hallucinate that these primitives are literally embedded into the body. And this embedding process is been partly explored in the thesis, but there's much work to be done in this area, and I'll show you what progress we've made. But the intuitive process is that we can hallucinate that these primitives are embedded in the body in this way. So there's a vertical hopper in the shank here, and we embed the stepping primitive in the hip actuator that's available to the robot. Similarly, for the quadruped, the bounding quadruped, we hallucinate that there's a pogo stick over there, composed of those two primitives, and another one over there. And we add an aspect of attitude control to stabilize its role. And similarly, for the monopedal hopper, again, we hallucinate that there is a vertical hopper and a stepping controller. All right, so that was the motivation, but now let's talk a little more in detail about how this process is going to work. Okay, so we've kind of seen the intuitive process, but we need formal guarantees about why they might work, and this process, I've tried to break it down to several conceptual steps. The problem with analyzing or getting analytical results for these hybrid locomotion-like systems is that beyond about 2 degrees of freedom, it's basically known to be impossible to get analytical results. So we had to develop some new tools in this area. So the first thing we want to do is think about steady-state locomotion as a system of coupled oscillators. So here's an oscillating spring mass, and you can see that I've drawn the phase plot over here. So what we'd like to do is, instead of thinking about it in these physical coordinates, is instead think about it in these phase and energy coordinates. So you can see very intuitively that the phase is the phase just kind of increases from left to right, and the energy, it wiggles a bit. It's been exaggerated here for parity, but the energy is something that we'd like to ensure stays roughly constant for the period of the phase. Now, formally, what this means is that we assert that the change in the energy with respect to the phase, so the energy dynamics is an order of magnitude slower than the phase dynamics, and this order of magnitude is given by S1. And when we have multiple oscillators, we have to intuitively kind of think about how their phases align. I've drawn the phase plots of these two oscillators now, and you can see that there's, so if I just look at their phases, the phase differences end up also being able to be slow coordinates, just as the energy was here. So here's an example of a more realistic system, the pogo stick, the 2 degree of freedom pogo stick, with a leg shank degree of freedom and a leg angle degree of freedom. And we come up with coordinate changes that turn each of these coordinates separately. So the green boxes refer to the leg extension, and the yellow coordinates refer to the leg angle. And as you can imagine, we can have these coordinate changes for each of those degrees of freedom separately, and then the task is to find appropriate phase differences that will let us appropriately analyze the system. So that's the procedure we use. We find these coordinate decompositions of coordinate changes for each of the degrees of freedom, and so we have phases and energies. And so now, before we move on, if you kind of step back and think about what the system now looks like in its full state space, we have this we have some hybrid limit cycle where here's the guard set where the continuous dynamics is interrupted, and there's a reset map, and there are these two special submanifolds of the continuous dynamics. The R, or the regulated subset, is where I'm saying that all of the energies are stabilized to their desired values, and the neutral submanifold is where all of the phase differences are at their desired values. So the point of bringing this up is that if you have these intuitive ideas that I want to regulate my energies and I want my phase differences to be aligned, that essentially puts you on the limit cycle. So the intersection of these two submanifolds should really be your desired limit cycle. But the problem is that the continuous dynamics in these nonlinear systems is not so kind, because neither of these manifolds will be invariant or attracting under the continuous dynamics. So that's obviously a challenge for analysis. So our solution is to come up with a new tool that lets us find an approximation of the continuous dynamics where this might be true. This procedure that I've used is a hybrid port of dynamical averaging, which is a theory for analysis of systems of two different timescales. So yeah, so if you have a system with two different timescales, intuitively you should think about phase as being fast and everything else being slow. And if you have a periodic vector field, the procedure says that an allied system with the average vector field, so you average the vector field over the phase, will give you an n-1 dimensional, so you remove the phase now, you've integrated over it, system which has a fixed point that's closed and equivalent stability. So this allied system, which is reduced dimensional, and you've gotten rid of the phase dynamics, has the same stability properties as the original system. So this is much better depicted visually than verbally. So I've taken my vertically oscillating system here, and I've plotted the original system and what the average system would do in this simple example. You can see that the average system, the red lines, do a very good job of capturing what the blue system is trying to do, but is obviously much simpler. And what we've done is ported this over to hybrid systems by simply introducing a reset map now. And what we do is we average the continuous dynamics, but leave the reset map intact. All right, so then the last piece, which was missing, is the part that I mentioned earlier, where we have to find these coordinate changes, and that's often very hard to do. And the last concept we've introduced here to be helpful is a time reversal symmetry. And really, the reason this is so powerful is that almost all of these local motion systems that I've looked at have some symmetry properties that can be used and leveraged to aid this analysis. So here's a description from Raibert's book of his ideas of symmetry, or his notion of why symmetry was important. Here's a galloping cat. A gallop is a typically very complicated gait, but even that you can see has this, as time goes down and you look at the reverse time behavior and mirrored, there's this kinematic correspondence of what the cat's pose looks like as you reverse time and some aspect of space. He also observed this in his own robot. So here's a picture of the leg extension and the leg angle, and you can see that the leg angle has a very clear odd symmetry and the extension has a very clear even symmetry. But the thing is, we can actually go much deeper than this. So there's much deeper than just these kinematic observations. There's a notion of reversible systems that's been observed, or physicists have thought about this for a long time, and Schwind and Todicek actually first introduced that idea in robotics, but it's really a property of the dynamical system where symmetry operation on the states is time reversal symmetry operation on the states is respected by the vector field in Hamiltonian or energy conserving systems. The benefit for us for this process in averaging is that we've developed a procedure by which we can automatically find these averageable coordinates and these phase differences that I talked about before. So for instance, we take the traces, so these are the traces of essentially, you can think about the leg extension and angle combined and taken over various times. This is from Raibert's book again. So we can automatically find phase differences from the 2 degrees of freedom states here, and essentially what we find is that the phase difference coordinate, corresponding with the neutral submanifold we talked about, is exactly 0 when you have these symmetric orbits that we would like to get. So this is very helpful. For instance, now we can apply this idea to slip. I'll just show you a small snippet of the analysis here, just to show you how the symmetry can really aid the analysis. So I've just drawn I've just written out the energy dynamics in the original slip system here. So remember, AR, the green is the shank energy, and the A theta, the yellow is the leg angle energy. And after we average appropriately, we are left with a much simpler system where you can see that there's no average change in the leg angle. So even though it's going through this procedure where it's getting tugged down by gravity on one side and on the other side, on average through the stance, through these neutral stances, the effect is zero. So I mean, intuitively you kind of expect that, but the analysis actually shows things like that now. And I've now drawn the Shank energy as a function of the Shank phase, and you can see the blue lines. The blue lines are the original system, and the brown lines are the average system. You can see that this averaging procedure gives us very appropriately simple, but simple dynamics that capture the original system very well. So the analytical benefit, one of the huge analytical benefits of this procedure is that, so I showed you how we can get fixed points that are closed. We can get stability, so that's the linearization of the return map. We can get that analytically, but we can also get an approximation for the return map itself. So let's go back and see how this is useful. So the averaging procedure, we're thinking about these phases and their frequency. The frequency is essentially phase difference dot, or phase dot, or the difference. Let's call omega of the relative frequency of the leg angle with respect to the shank. So essentially, it's capturing how fast my leg shank is spinning versus the frequency of or how fast my leg angle is spinning with respect to the shank dynamics. So the shank phase maybe has some evolution through this interval over here. What we now do to set the touchdown angle of the leg for the following stance phase is we use this idea of what the relative frequency is, which averaging gives us an explicit formulation for to essentially find a near deadbeat solution to this touchdown angle. So essentially, what we're doing is using an approximation for the return map to get a deadbeat solution, or approximately deadbeat solution, for what the touchdown angle should be. So Raibert had his own idea of how to do this. Maybe you didn't think about it this way before, but essentially what Raibert was trying to do with his stepping controller, and I apologize for people who aren't intimately familiar with this, but there are many who are, but this procedure that Raibert used was essentially trying to get a deadbeat control on the stepping angle, with the deadbeat approximation being a very crude one, where it was just derived from the forward speed of the body. What I've done is I've simulated both of those systems, and essentially, so this hopping system is trying to attain 1.5 meters per second as its desired speed, and using the averaging provided return map approximation, we're able to get much closer to the desired speed, even withstanding all the approximations that were made, than the naive approximation that Raibert's stepping controller provided. That's one of the benefits of this analytical procedure. So taking that analytical procedure, yes?
What is the role of that proportional control? Because by increasing the proportional control, maybe you can increase the error and achieve the same performance.
Yeah, no, the proportional controller is actually acting, but there is some persistent offset. So one of the reasons that there is a persistent offset for the averaging case is that, firstly, we're not guaranteed that the average system will have the exact same fixed point. It's supposed to be epsilon away, and it's very hard to quantify exactly what that is. So we can't actually do that quantitatively. But what we find, for a variety of examples, is that the fixed points are fairly close. And the second thing is that this approximation for the deadbeat thing is, it's not exact. It's an approximation. So there's, every step you're making some mistake, and the proportional controller is trying to catch up. Oh, so yeah, sorry, this thing is exactly this. It's just proportional controller on the speeder. So every step it's making a mistake, but that mistake was smaller using this return map approximation. Oops.
So do you use the same proportional?
Yes. Okay, so I've taken all of that analysis and been able to create something like computational procedure. So the first person who's been, a guinea pig for this is a master student, Aziz, who's been working with me and Dan. But I've been able to use this procedure for all of the proofs that are in the thesis. So it looks kind of ugly, but essentially the input of this procedure is that you have a closed loop vector field for the body in these special coordinates, so that goes in as an input here. And the output is really an expression of the return map Jacobian and its eigenvalues. So you put in the system and you get out if it's stable or not, which is pretty nice. But obviously so either you'll get stability or instability, which is a good conclusion to have. But obviously there are various places where it could go wrong. So I've tried to articulate all the known places where it can go wrong. For instance, one of the problems could be that there's a persistent dissipation in the continuous dynamics. An example of this, I'll actually give examples of this maybe at the end if there are questions, but that's one of the criteria is that we need an equilibrium of the vector field to perform this analysis. So if there's persistent dissipation, if the vector field isn't in an equilibrium, then the procedure will fail. Another reason is that the reset map, so remember this is a hybrid system, the reset map must have some Lipschitz properties. Otherwise, if the reset map is perturbing you too much, it kind of just wipes out intuitively, kind of just wipes out what the continuous dynamics is doing, and your conclusion with averaging is basically useless. Another problem is some of we were talking about oscillators. If their frequency goes to 0, that's not an oscillator anymore. So you can understand why that might cause numerical issues in the procedure. And lastly, if the return map is not hyperbolic, obviously we can't make any conclusions because structural stability is necessary for us to be able to because we get an approximation that's slightly different from what the original system would have been, and if the return map wasn't hyperbolic, that could make the difference between stability and instability, so obviously we need structural stability. So we have potential fixes for all of these, which are articulated in the thesis. This last one is particularly interesting. So lots of these locomotion systems seem to have, kind of marginal stability properties in some of its dimensions and states. So it's possible we could exploit and find cyclic variables before we go into this averaging procedure and remove those marginally stable portions of the states before dumping into this procedure. All right, so I am going to have to skip some stuff. So the slot hopper I showed you guys last time. What I'll do is instead show you. My committee made very helpful suggestions last time I gave the proposal talk, and one of the suggestions was that I described some of the analytical results we get. So you remember the slot hopper was the bounding and the trunking virtual biped, and some of the results we can get, for instance, in this domain are that essentially, I should really, sorry, I should really show you a little bit of this other slide first. Okay, so for this virtual biped, what I've done is I've taken the parameterization of its physical design on this axis, which corresponds to where its mass is concentrated. So the red dots you should think about as the mass concentration on the body of this virtual biped. And what I've done on this axis is I've plotted the stability of its in-phase or anti-phase coordination as it's allowed to bounce. So what we find is that as the mass parameterization changes from mass concentrated within the hips to mass outside the hips, there's a sharp phase transition in whether the anti-phase alternating limit cycle or the in-phase limit cycle is stable. And we see this on the robot as well. So here's our Minotaur robot, which lies here on the parameter spectrum, and sure enough, it coordinates anti-phase when commanded with vertical hoppers on its hips. Similarly, when we now add to its inertia by physically modifying the body, so you see we've added some masses to the body such that its inertia is now much higher. It lies in this area. Now, without any change in the control signals, it would like to prompt. And what we've done in addition is develop control strategies that modify these tendencies that are guided by the body design to cause it to, on one hand, take the prompting minotaur and cause it to bound, and as well cause the bounding minotaur, which lies on this side, and make it prompt. So this work was empirically motivated, but we also, with the analytical tools that I just described, we can actually get the same stability conclusions, and I understand its relation to that inertia parameter. So what we do, remember this figure, so what we do is think about, so this axis is that inertia parameter kappa, where 1 is exactly, where the phase transition happens. So we think about this kappa as being related to our epsilon perturbation parameter. So as we move kappa from 1 and backwards, as an epsilon perturbation of 1, so you can see that here, our analysis tells us where the fixed point of this epsilon perturbed system is, and we can then get the return map linearization, like I described with that computational procedure, and we can get eigenvalues that show that it's all 3 eigenvalues are stable. So remember, this is a 2-degree of freedom system. The return map has 3 dimensions, so 3 eigenvalues. So we can get 3 stable eigenvalues as we perturb epsilon, and that includes this body parameter kappa from 1. The other an analytical result we have is taking now this kappa and making it much higher than 1, so pushing it much higher this way, and with an assumption that the pitching energy is low. So we start with low initial pitching energy. We can firstly show that low pitching energy is invariant. So if you start with low pitching energy, it doesn't increase. And secondly, what we can show is that there's a rough decoupling of the vertical dynamics of this prompting body with the pitching dynamics. And we can show that the vertical dynamics are identical to an isolated hopper. So in the prompting body, the center of mass just looks like it was a vertical hopper. And we can also show that the pitching map, just the pitching dynamics has a stable return map. And also we have analytical results to show that when kappa equals 1, we can introduce these phase controllers, which is given by the red and blue dots, and that will give us feedback-driven stability on the return maps. So these are all analytical results that inform the empirical aspects that I showed you with the slot hopper. Get back to where I was. All right, I'll just talk very quickly about this Raibert robot, and then I'll go on to the conclusion. So we've seen this robot do tail hopping before, and essentially the behavior empirically now is constructed using very similar ideas. So we imagine there's a vertical hopper on its leg, but it's now energized by the tail. So this robot doesn't have an actuator extending the leg shank. Instead, what it does is it uses its tail to add energy similar to what an actuator would have done if it were in the shank. And then what we do is we compose that stepping controller, which we talked about quite a bit today, to get hopping in the plane. And lastly, we can also now add an aspect of stabilization of the body attitude, which is caused by torques exerted by the hip joint in stance, and we can get hopping in the plane. All right, so one aspect of Raibert that's very interesting in relation to my modularity arguments that I really wanted to show you, which is why I went to these slides, is that this Raibert robot can actually exhibit 2 different kinds of solutions to the same composition. So let's just take hopping in the plane. So this is the tail-energized hopping that you saw in the previous slide. It's an animation, if you couldn't tell. And we've also obviously seen this on the robot as well. But it can also exhibit this hip-energized hopping, where now you can see that the tail is not moving very much, and the hip is powering the locomotion. And we've been able to replicate this in very limited instances on the robot. And you can see here's one such instance where the tail is actually poking against the ground And I'll show you why this is difficult on the robot as well. So when we look at these simulations, what we find, so the red is the hip energized and the blue is the tail energized, is that even though they're both, hopping in the plane, so you can see the height is kind of oscillating, and there's some non-zero speed, they have kind of different characteristics. So with the hip energized hopping, we get much higher speed, which is kind of reflected both in the simulation and the empirical result. But we get much higher normal forces, noticeably higher normal forces in the tail energized hopping. And one of the reasons that this behavior has been hard to replicate on the robot is that the available traction with the reduced normal forces, the red ones are reduced, is not enough, so the legs slip. The simulation doesn't have that problem, which is why it's much easier to develop this or demonstrate this hip energized hopping in simulation. All right, just to recap, higher speed, higher normal forces. So you can imagine there are situations where you'd want the robot to autonomously choose between different solutions, for instance, if it were on ice, or if it needed to get somewhere quickly, and we're trying to push towards a notion of synthesis which allows for this kind of granularity and modularity. Okay, now I'm going to go to the conclusion, and so firstly, let's kind of go back and revisit our motivations to see where we got with all this work. So this is what I said that we wanted: structural stability and generalizable solutions. And what I've done here is kind of broken out these into subcategories. What our desired outcomes were in black, and the progress we've made so far in blue. So what does structural stability mean? To me, it means at least these two things. So firstly, you must have guarantees of stability, and secondly, you must have robustness to perturbations in parameters as well as states. And what does generalizable solutions mean? So firstly, we would like an efficient synthesis procedure which doesn't need. So the efficient synthesis. So we would like to not go back to the drawing boards every time we'd like to synthesize something new. We would like behavioral complexity. We'd like to get multiple behaviors. We'd like to, we learn how to hop once, we don't want to learn it over and over again. And we'd like this granularity, where if there's a particular module that's ineffective, if the hip energized hopping is ineffective on ice, we'd like to be able to swap it out without changing everything about our synthesis procedure. So what have we got? So in terms of stability guarantees, we developed this hybrid averaging procedure, which gives us eigenvalues in that procedure I showed you. In terms of robustness, there's not formal, but there's plenty of numerical and empirical evidence, some of which I had to unfortunately skip, but we talked about the sleeping robot, and so that's an example of a not persistent but large perturbation in its states. And we've also given it persistent perturbations in the form of coupling it with additional primitives. So, for instance, the slot hopper, which was coordinating two vertically hopping legs, was then composed with fore-aft and yawing perturbations, and continued to work. In terms of the efficient synthesis and behavioral complexity, this was one of the first things we talked about, is how a few templates can really give us a diversity in the types of bodies that we can address. And lastly, we talked about how if a particular module isn't working well, we can try and swap it out. So that's sort of, I think, what the progress has been made so far is, but it's really very much a work in progress. I really see the PhD work that I've done, that I've presented here, as not being completion of anything, but really an attempt to articulate a problem that's been hard to articulate in the past, and really setting up a lot of future work in this area. So I guess that's the end of my material. I'll quickly give you an overview of the other research I've done in the lab and how it relates to the stuff I've presented in my thesis. So we talked about all of these things, briefly at least. Now I've done some other work on, for instance, approximate Bayesian estimation. So we looked at how, talking about approximations here, there are also approximations there to think about how to approximate belief distributions, which can get very nasty in high-dimensional spaces. with piecewise constant versions and still prove that estimators converge. Instead of having this kind of conventional sense plan act version of navigation and planning, we really worked on closed sensory motor loops that take sensors and controllers all at once, and also allow actuators to modify our sensing, so active sensing. And we also worked on some non-cyclic tasks, for instance, orientation, inertial reorientation with the tail in the roll plane and in the sagittal plane for this Raibert robot, as well as leaping with the tail and the leg that you saw briefly. All right, so yeah, these are not in my pieces, but we talked about all of these papers over here. The blue ones are journal papers, and the black ones are conference papers. And this paper, it's unfortunately still in prep, but it's very close. And this is the paper that's going to describe how time reversal symmetry can simplify getting averagable coordinates for our systems. I guess that's the end of my talk, and thank you all for coming. I'd really like to thank my lab mates and my family and friends who weren't able to be here today for their support throughout my thesis. Thank you. And my advice right there, of course.
The first part, we'll ask for questions from the audience.
Very happy. So, beautiful presentation.
Oh, thank you.
And a couple of sort of quick things I'm kind of curious. You mentioned briefly that when you're talking about the templates, you briefly mentioned that these would, by design, be 1D. Is that a limitation in any particular way?
No, I really don't.
Needs to happen.
No, there's no reason that needs to happen. In fact, there are 2 degree of freedom templates. For instance, the inertial reorientation. Oops, that's enough. Yeah, this inertial reorientation thing. There's almost no way to. There's almost no way to reduce this one to a 1 degree of freedom template. So that procedure is describing how to correct both the tail angle as well as the roll angle of the body. That seems to be inherently a 2 degree freedom problem, even in its most irreducible form. The templates themselves, I didn't talk about this much during the slide, but there were a few that I developed that were handpicked that showed up, obviously, in the second column of my figure 1.1. But I really think a future area of work might be to identify. So find these primitives from animals, from humans, from other sources of data, so that we can understand what useful primitives are. One of the modes of failure of my computational procedure that I listed was essentially boils down to the wrong choice of templates. So that's definitely an area of future work. We'd like to find more templates.
And the 2D, when you use a 2D template, this machinery that you develop and generalize naturally.
Yes. Yeah.
Okay. I have another question, but it's okay. I can
Go for it.
Okay. So you kind of already addressed this. The other question was about the limitations of this sort of Hamiltonian assumption that you're making. And you do specifically say that in one case, one of the known failure modes is you have dissipation that you couldn't deal with. So you kind of already answered the question that I'm struggling to formulate, but the question is essentially what are the limitations, or where does this thing break down?
Yeah, so first, I think I should clarify, so that I don't actually assume things are Hamiltonian, and that's one of the reasons that this is hard. Let me go back to this slide. So I actually don't, so in this vector field, let's go back to the beginning of this slide. So in this vector field, you can see that, all of these epsilon terms that are explicitly added in the vector field are essentially supposed to capture dissipative terms. So I don't assume that it's Hamiltonian. The only exception, which is the limitation that I mentioned, is that I assume that on the limit cycle, the continuous dynamics doesn't dissipate. So there's an equilibrium of the vector field at the limit cycle. But depending on how you choose your coordinates, that may not be true. So for instance, I'll give you an example. So if you think about a classic rimless wheel, which is a system that's accelerating through its continuous dynamics but having an impact when it's hitting the plane. A naive idea of energy would always have the energy increasing in its continuous dynamics and dissipating in its discrete dynamics. So that's not accounted for yet, because I need my analysis to be about an equilibrium of the vector field. Now, having said that, it's entirely possible, and I think quite likely, that you can change coordinates to a system where there is an equilibrium of the vector field in that situation. So that's obviously something that needs to be addressed.
Thank you. The other thing is your selection of those templates seems to be, you are looking for a coordinate transformation with minimum coupling. So is there a way to justify that, you have the actual system model and a set of templates, can you just make a decision, is this collection of templates a good descriptor of that system based on that coupling between those?
Yeah. So right as of now, there isn't a way to make that assessment other than going through this procedure and finding out that one of those failure modes were hit. So one of the really big areas of future work, I think this is one of the aspects of this kind of morphological computation that I think really accompanies and complements this work, where I haven't thought about the morphological computation aspects at all. Or morphological selection, I guess, of templates, as well as how the control inputs enter the templates. So that whole area is kind of a very ripe complement to this area of research, I think. I think your question really falls squarely within that category of understanding how the templates embed into the anchor itself. Unfortunately, this work so far doesn't address that question. So for me, it's been very much a apply and tech in this procedure. It's definitely an area of future work that's pretty easy to articulate.
Especially to explain that, for example, if you have such a collection of templates for miniature, why it doesn't work for X?
Yes, right.
Also, the other thing is, do you have any because I guess there is a kind of a backward direction as well, how those selection of the templates for your model influence the mechanical design, because I think was aware about that. You have some control strategy in your mind and you design your system based on this fact. So can you make some comments regarding this?
Yeah, so design is hard to parameterize. So in as much as the design parameters are continuous scalar parameters that appear in modeled dynamics, those are easy to see how they affect the stability. For instance, that kappa parameter in the Stockhopper that I talked about quite a bit. So that clearly the analysis says how that relates to the end result. But things like, for instance, when I talked about the gerbeau, it has a tail instead of an additional degree of freedom, and that's pretty hard to parameterize in some kind of continuous way. So unfortunately, we can't make that kind of morphological conclusion or decision yet based on analysis. But yeah, maybe some aspect of future work will get into that.
So if we go back to the picture you had of the phase energy plot manifold,
yes,
intersecting.
Yeah.
So my question is, are there systems where the intersection of those manifolds might be more than just a one-dimensional limit cycle, and would that potentially cause any issues?
That's very interesting. I've always been thinking about steady-state behavior as limit cycles is admittedly a limited way to think about it. If you restrict yourself to thinking about steady-state behavior as being a limit cycle, then you're only going to be left with a one-dimensional intersection. However, I don't think that's necessity. Steady state behavior could be not, it could be chaotic, or it could be, I don't know, in some weird knotted topology or something like that. It just has to be periodic, right? And S1 is not the only way to get a periodic embedding of dynamics. So that's an interesting. So that's very interesting, but I haven't seen it in kind of a simple hopping and running with low numbers of flex so far.
Although some of us suspect that your walking thing is a minimal set rather than a limit set.
Yeah, that's true.
Some of us suspect that that's an instance of your
I've been very clear to talk only about the hopping and running, which are very easy hybrid limit cycles. But yeah, we've worked extensively on a walking gate for Minotaur, which is analytically much more complicated because it has it seems to kind of wander around a variety of limit cycles and has interesting stability properties. So yeah, maybe that will come into play for that.
Okay, thank you. This concludes, I guess, the public part of the defense. You can just wait outside. Thanks a lot for attending, and
Jesse, are you still on the line?
I certainly am.
You're a hero. You're a hero. Thank you. We're moving. If you didn't hear, we're moving into the